Hello, good evening. There's a reason why I crash into the board so awkwardly at this. It's because it will help introduce us an analogy for a way to quickly remember and understand how to use Cramer's rule to solve any system of linear equations, which could also be a matrix equation, and anything for that matter. So in the level of abstraction we want to deal with, we have an input vector here, x, and it's being transformed by this transformation matrix, which is invertible. It needs to be an invertible matrix. Therefore, your matrix must be an n by n matrix. In other words, it must be a square matrix, which therefore means you have a non-zero determinant. That just comes from the invertible matrix theorem, which is has many properties to move it. And then once you transform that input vector with that transformation matrix, you get this output vector here, B. So I have an example here of how we'll solve for these components for this column vector x, input vector x, x1, x2, x3, x4, x5, transformed by this supposedly hideously looking like matrix here. And the gist of what we're going to use is this here. This is what Cramer's rule is. We're basically taking the ratio between two determinants. Now, I'm going to hope and assume that you know how determinants work prior hand, especially in the way that they geometrically in the coordinate plane work either as areas or volumes, and therefore if you multiply by determinants, you're basically scaling some abstract geometric solid by that amount or factor, the dilation in this case. But basically, the gist of what Cramer's rule tells us is, first we have to calculate the determinant of this matrix here, which, fortunately for us, is a triangular matrix, an upper triangular matrix. And as a result, there's this easy theorem which tells us that we can just find a determinant by multiplying the diagonal entries only. So then the determinant of A is just 1 times 2 times 3 times 4 times 5. In this case, this happens to be the same as 5 factorial, which would be 5 times 4, 20, 20 times 3, 60, 60 times 2, 120. Okay, so think of, I forget whether it's the determinant AI or determinant A. One of these is going to be the original volume area. Eventually this generalizes to any n by n matrix, so we can't really describe a nice geometric construct for this, but this thing will be dilated by this amount, determinant of AI here. And how do we create this AI? Well, this column matrix, 1, 1, 1, pretend this is a car, and this is either a parking lot or we're in the traffic jam, in the middle of traffic. So I even go and draw here a bunch of nice cars on the side here. Vroom, 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 vroom. Vroom, 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 vroom. Yeah, they're all sardine packed. And just think of this 1, 1, 1, 1, 1, 1 column vector in another lane. He's becoming an angry airhead, hothead, which is particularly, well, I don't think this kind of behavior is typical like in Thailand where I'm from, but maybe in like New York or some other capital city. Guy has anger, hothead issues, and so he decides he's going to drive from this lane over here and slam, pow! into one of these column vectors and displace it all the way up into the side so that he can take its place. So we would create a special kind of matrix, A1, which would just be this entire thing, except with this column replaced by this guy over here. So we're going to get 1, 1, 1, 1, 1, and that's going to be 6, 2, 0, 0, 0. Sorry, yeah, just making sure it's all right. And then we have 10, 7, 10. Oops. 7, 3, 0, 0. 13, 11, 11, 8, 4, 0. And then 15, 14, 12, 9, 0. Now, if you use whatever favorite algorithm you want, in this case, for me, it's like Gaussian row reduction. I actually put it into a calculator, and put it into an upper triangular form. We end up with, to 2 decimal place precision, the following equivalent matrix. 15, 0, 0, 0, 0, 10, minus 6, 0, 0, 0, 6, minus 3.6, minus 2.2, 0, 0, 1, 0.4, negative 0.0910, 13, negative 3.8, 0.340, 0.48. And then we can find the determinant of this upper triangular matrix by the same way, just by multiplying the diagonal entries. So the determinant of A1 equals 15 times negative 6 times negative 22 times 1 times 0.48. And now I need a calculator here. Give me a sec while I do this. Let's see. Okay, so that rounded to 2 decimal places is around negative 4.19. No, that would round up to negative 4.20. Nice. Oh wait, no, that goes to 69. This is 42. But yeah, you basically get this column vector here. You car crash into all of these other vectors, and then you replace it with that. So then in this case, for the x1 solution in particular will be a determinant of a1 over the determinant of a. Let's write some better notation here. So this would be negative 4.2 over 120. And that, and I might keep the numbers the same, I might not, who cares? So the precision, I mean, so negative 4.2 over 120, that's negative 0.035, so that is x1 here. And we proceed to do the same steps with all the other remaining 4 columns of this 5x5 matrix here. So, I'll repeat again in these steps here. Cramer's rule, we have for finding a fraction between 2 determinants, so denominator determinant hope I got this right, is the initial object, original determinant, and then the numerator is a dilation transformation that stretches or compresses your matrix set of vectors. We form each AI, and I'll just use the words of the analogy that I use, by taking column vector B and road rage crashing into the ith column. Of our transformation matrix A here. Let me write that lowercase b here. Then proceed to take the computation determinants and then, do the same results, and we'll get our answers, which either will be approximate or they'll be exact in this case. So, oh shoot, I already erased the thing. But, where was it? Negative 4.2. Okay, yeah. So I just ended up getting that determinant of A1 is around negative 4.2. I will quickly draw for you. Actually, it was going to take a bit of time to draw up. But I'll quickly draw for you what the other A2, A3, A4, and A5 matrices are going to look like, and their upper triangular matrix equivalents. I hope you memorize this part, the key thing here, because now I'm going to go and erase this part now. Okay, ready? 1, 2, 3, bye-bye. We have A2 as 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, 10, 7, 3, 0, 0, 13, 11, 11, 8, 4, 0, 15, 14, 12, 9, 5. That becomes the upper triangular form of 15, 0, 0, 0, 0, 10, minus 6, 0, 0, 0, 13, minus 3.8, minus 2.22, 0, 0, 1, negative 0.6, negative 0.00, there's some missing precision stuff here, negative 0.7, 0, 1, 0.4, 0.44, negative 0.02, 0.03. So then the determinant of A2 here equals 15 times negative 6 times negative 2.22. Oh, no, sorry, negative 2.2 times 1 times 0.48. Let's get A3 up here. A3 is 1, 0, 0, 0, 0, 6, 2, 0, 0, 0, 1, 1, 1, 1, 1, 13, 11, 8, 4, 0, 15, 14, 12, 9, 5. Upper triangular, it becomes 15, 0, 0, 0, 0, 6, minus 4.8, 0, 0, 0, 13, negative 2.4, negative 3.3, 3, 0, 0, 1, negative 0.8, 0, negative 0.33, 0, 1, 0.2, 0.58, 0.03, negative 0.1, 0. A4 will become 1, 0, 0, 0, 0, 6, 2, 0, 0, 0, 10, 7, 3, 0, 0, 1, 1, 1, 1, 1, 15, 14, 12, 9, 5. So upper triangular becomes 15, 0, 0, 0, 0, 10, minus 6, 0, 0, 0, 6, minus 3.6, minus 2.2, 0, 0, 1, 0.4, negative 0.09, 0.44, negative 0.00, 1, negative 0.6, negative 0.7, 0.00, 0.27. And then A5, it's already going to be an upper triangular matrix, so we don't need to do an extra transformation here. So A5 would be 1, 0, 0, 0, 0, 6, 2, 0, 0, 0, 10, 7, 3, 0, 0, 13, 11, 11, 8, 4, 0, 1, 1, 1, 1, 1. So the 1, 1, 1, 1, 1, 1 output vector decides to be an asshole and crash all these guys out the way. So yeah. Okay, determinant of A free is, let's see, that's 15 times negative 4.8. Yeah, 4.8, right? Yeah, 4.8, negative 4.8 times, I lost track of, negative 3.33, negative 0.33, negative 0.10, determinant of A4 equals 15 times negative 6 times negative 2.2 times 0.44 times 0.27. And then determinant of A5, it's going to be a new different thing. It's 1 times 2 times 3 times 4. Yeah, so it's 4 factorial. 4 factorial, so it's basically this 120 divided by 5. Which, let's see, can I do mental math today? It's going to be bigger than 20. Looks like I'm just going to have to do okay, 24. 24. That gives a nice number for this, and then the approximations for these, I'm just going to, please give me a second as I go to my calculator. So that is 95.04. this one here. That's going to be 7.91. That's going to be 235.22. And then we're done. We're done. So at the end of the day, we write down our solutions, which are just fractions of determinants. The determinants that's being bullied by the column vector, our output vector here, and then the original determinant. So this guy's a bully. He's mean. Oh, I can't draw that. There we go. He's mean. Bully. And so xi again equals determinant of ai, which just you replace ith column with output vector b over determinant a. And so x1 will be negative 4.2 over 120. x2 equals 95.04 divided by 120. x3 equals 7.91 divided by 120. x4 equals 235.22 out of 120. And x5 equals 24 out of 120. And can I simplify this? See if I can do some quick arithmetic mental math here. 4 times 6, 4 times 3, but in the end it won't really matter because like I'm not going to simplify this crap anyways. Just do 1/5. Yeah, nice exact answer for that. But yeah, that's your solution set. And yep, we got this all to the power of traffic jams and road rage. If you have any problems still trying to understand this video, I highly recommend look at Free Blue One Brown's Essence of Linear Algebra playlist, particularly not just Cramer's rules section, but determinants and dot products and duality. Otherwise, I think I've covered a thorough example of how you do this and a nice way to memorize it. Again, car crash. And yeah, I don't think my country, like, traffic is gonna let up anymore, and I mean, we get a couple of people fast cutting lanes, but no insane car accidents yet, fortunately. So I'll just leave it at that. So yeah, I hope you understand and like this little analogy I had for understanding how Cramer's rule works. Until then, I will see you in the next video. Goodbye.